Thank you very much. Thank you for inviting me to this Blue Water Symposium, and thank you all guys for being here. So I'm going to try a little bit, something a little bit different, namely kind of give two talks in the time that I've been allotted. And part of the reason for that is that while one of these talks is in itself very interesting, the other talk is very new and some stuff that we should, in fact, introduce to the astrophysics community, namely the fact that geodesic mesh MHD and the conveniences that it offers is now a reality. So I'll go ahead and talk about both topics. So let's go ahead and talk about the first topic first, which is turbulent two-fluid dynamos. And from the viewpoint of a plasma physicist or an astrophysicist, a dynamo is basically any process that increases the strength of the magnetic field in a plasma. So these plasmas tend to be threaded by magnetic fields, and we want to amplify the strength of the magnetic field, but we also want to amplify the coherence length of the magnetic field. Namely, you start with little loops of magnetic field, you want to build up large coherent structures. Now, there are two traditional dynamo mechanisms. One is the large-scale dynamo, which operates very slowly, but there's another dynamo, which is the focus of this talk, which is the small-scale dynamo, and it's kind of more interesting because it's more ubiquitous. All astrophysical systems have turbulence in them, and therefore they actually support the growth of a small-scale dynamo. Now, over many years, dynamo theory has been worked on, but it was actually worked on within the context of ideal MHD turbulence. And unfortunately, it turns out that in many astrophysical situations, we want to actually understand the operation of dynamo in partially ionized plasmas because many astrophysical systems, whether molecular clouds, the interstellar medium, and so on and so forth, are in fact partially ionized plasmas. So we want to understand dynamos and their evolution in partially ionized plasmas, and this problem has never been studied before. Now, it turns out that a couple of theorists went to town and actually understood or worked on the theory of partially ionized plasmas and the dynamos that they could support in them. And they actually found out that there were some very important predictions that were unique to partially ionized plasmas, which does not actually happen in fully ionized MHD turbulence. And so what we've done is we've put a lot of computational resource to actually verify that those predictions are in fact verified, which is a good thing because it basically ensures that on the one hand we have salient theory, and on the other hand we have good high-resolved computations that can be analyzed by the theorists. We'll actually, these things have actually a lot of applications to molecular clouds and early universe cosmology also. So let's go ahead and ask what happens in a small-scale dynamo. And essentially what happens is that you start with a loop of magnetic field, some turbulent process stretches it out, another turbulent process will kind of go ahead and twist it and make it fold on itself, thereby doubling the magnetic field in this region. But of course, there's old work by Coulter and Anderson, which says that if this process were to continue, the magnetic field on small scales would grow to the point where it would basically quench off all turbulent motions. So that was the state of affairs, but along came Lazarian and Vishniak in 1999, who basically provided a way out, which was to say that they found that magnetic fields could turbulently diffuse on each other on length scales that are even larger than the resistive length scales. And this actually opened the door to supporting the idea that you could have small-scale dynamos in a single fluid, fully ionized medium. However, the picture needs to be modified very significantly when dealing with a two-fluid, partially ionized medium, because in such a medium, the turbulent diffusion cannot operate. In fact, the first non-ideal effect that you run into is ion-neutral friction, which actually provides a small-scale dissipation. And as a result, the ion-neutral friction is very inefficient for a plasma that has only a very tiny amount of ionization fraction in it, which is what actually happens in molecular clouds and also in the primordial universe. And so you actually have to deal with the fact that there are very infrequent collisions and therefore very inefficient conversion of kinetic energy into magnetic energy. And the propensity for small-scale equipartition is therefore dramatically reduced. So with that, you basically ask, what are the length scales on which these two equations, one for the ions and one for the neutrals, would produce a significant amount of coupling via these terms? And the answer is that the length scales, there's a certain length scale called an ambipolar diffusion length scale. And this length scale actually increases as the ionization fraction decreases, and furthermore, as the magnetic field grows, this ambipolar diffusion length scale on which the ions and the neutrals decouple actually increases. The upshot of that is that you have a situation where these calculations become unusually difficult because the dynamos grows unusually slowly. Now, the theorists had already made a prediction, and one of their predictions was that if you have magnetic field as a function of time, they anticipated that you would first have a phase of exponential growth, but at some point, the ambipolar diffusion length scale matches up with the driving length scale, and then you past that point, you have a linear growth in the evolution, and of course, eventually you will have saturation. So what we actually did was do very high resolution simulations. These might not be high resolution to others, but because of the amount of time steps that you have to take and the amount of grinding you have to do in a dynamo simulation, they're amongst the highest resolution two-fluid dynamo simulations that were ever done. And Blue Waters has been a unique machine for enabling us to do that. We wouldn't have been able to do that on any other Exceed resources, and the Blue Waters team was amazingly cooperative in helping us to do that. But the nice thing is that both the predictions, that the first prediction of the initial evolution as well as the late time evolution was actually borne out by the simulations. The theorists also made a further prediction, which is to say that initially the peak in the turbulent energy would focus itself on the smallest scales, and as time evolved, this peak in the turbulent energy would actually migrate to larger scales. And this is actually showing you a whole stack of spectra at different times, starting from earliest time to latest time. And you actually see that trend of the evolution of the peak in the energy spectrum borne out in the simulations exactly as predicted by the theorists. Now, I could keep going on about this topic itself, but there's another topic that is very near and dear to my heart, which is why I actually like to talk about it. And the first of these papers in this series has actually been published in monthly notices, so I'll urge you all to look it up. And which is to say that astrophysical systems tend to be round. And it would be highly desirable if we could actually do MHD to the same specification that we do it on structured Cartesian meshes, if we could do it on the same specification, but on meshes that are optimally suited for spherical systems. And the inability to do that, or the refusal to do that, has many consequences, one of which is that the time step at the poles actually goes down. Now, of course, Tchaikovsky and even Burroughs and their groups have actually taken a stab at this issue. However, the other problem is that even the accuracy at the poles is degraded by the fact that you have a coordinate singularity. So wouldn't it be great if you could actually do MHD simulations on a mesh like this, where the triangles actually show you the mesh points and the mesh is completely isotropic? So this, if this were done, it would actually cure the two big problems, namely the time step and accuracy problems at the poles. And if we were able to do it, there are a lot of systems, astrophysical systems, which would benefit from this. And this is kind of an extensive list. But what do we actually have to do? Notice that these days we're actually moving in the direction of treating turbulence, which basically means that if you want systems, or if you want simulational capability which reduces the dissipation as well as the dispersion, you necessarily need to go to higher orders of accuracy. So that's the first thing that you have to do. And then you need methods that are actually 100% stable, even in the presence of strong shocks, while accommodating to the need for higher order accuracy. So delivering on all of those goals is kind of a hard row to hoe, and we've actually delivered on those goals recently in this paper. So how does this actually work? It works from realizing that the Greeks were actually onto something, which is to say that you take this icosahedron mesh, icosahedron, and you basically inflate it out so that it matches up with a sphere. This shows you that on this sphere you have 20 exactly uniformly distributed triangles. Now, of course, you can't do computational astrophysics on such a mesh, but you can refine this mesh. So you refine it one level, and you get this mesh. This mesh, again, is not necessarily perfect, but you can continue this process of refinement 4 levels onwards, and then you get this beautiful mesh out here, and our task is to actually do computational MHD with all the niceties that are attendant on such an exquisitely isotropic and uniform mesh. And of course, the third direction, it's a 3-dimensional capability, so the third direction is easy to achieve because you basically just extend everything outwards. So how is this whole process achieved? The answer is that we have higher order Vino reconstruction that has been extended to work on unstructured meshes. We have full divergence-free reconstruction of magnetic fields, which is essential for the computational algorithm as well as the adaptive mesh refinement. We have genuinely multidimensional Riemann solvers, which open the door to making this possible. And we have higher order accurate time updates. So we can actually achieve up to 4th order demonstrated so far, and there's no barrier to going even higher order. So we can achieve higher order accuracy, which is very important because for turbulent simulations, it is highly desirable to have very low dissipation and very low dispersion, which is only guaranteed by higher order schemes. And furthermore, this use of Vino reconstruction essentially ensures that we have ability to handle strong shocks, which are endemic in astrophysics. So I could keep talking about the algorithmic issues, but again, I will skip the details, except to show that this kind of gives you an impressionist understanding of how the Vino that we've designed takes the traditional ideas that you know of and extends them to higher orders on unstructured meshes. And furthermore, you want the solution, the magnetic fields are only resident in the faces of the mesh, but you want the solution all over in the interior of the mesh if you want to go beyond 2nd order accuracy, and that's actually achieved. The gold standard for structured mesh computations is this standard out here, where you have volumetrically centered fluid variables and face-centered magnetic field variables updated by edge-centered electric field variables. And what allows this transcription from here to here, which is what you need for spherical meshes, is exactly the multidimensional Riemann solver. And there's a whole slew of papers written on that topic also. And here you can see that on classical test problems, we're able to achieve this accuracy. So you can see that as the angular resolution is increased, or as the angular resolution is improved, the 2nd order accurate scheme goes at 2nd order accuracy, the 3rd order accurate scheme goes at 3rd order accuracy, and the 4th order accurate scheme actually shows full 4th order accuracy. So that's a good thing to demonstrate, okay? Scalability is perfect scalability on blue waters. It's one of the ironies of computational science that when you perfect something on one system, that system actually goes away. So that's life. But we have actually started doing applications. So here's an example of sub-Keplerian accretion flow taking place onto a central compact object. And typically, if you see the intensity as a function of time, it shows this periodicity. And if you plot it out, if you Fourier analyze it, it shows a clear existence of a quasi-periodic oscillation, namely the system actually breathes at a certain frequency. And that's actually easy and nice to demonstrate out here because you can actually see, I'm sorry. Okay, got my bearings. You can actually see the density, subcaplarian accretion flow coming in, forming a shock out here. The shock is a standing shock, and it forms a tiny accretion disk in the center after the material has flowed through the shock. You can actually see the evidence for quasi-periodic oscillations out here because you can actually see that this shows you the cut in the xy plane where the rotation is along the z-axis. And you can again see the formation of a shock, and the presence of the shock along interacting with the accretion disk gives you these breathing modes, which actually gives you a source for quasi-periodic oscillations. It's just one possible source for quasi-periodic oscillations. There are other mechanisms also presented in the literature. And now you ask, how can you actually form jets out here? And the answer is that if you start throwing in any sort of magnetic fields, and an example of such a magnetic field loop is shown to you out here, then you actually have the ability of having the magnetic field anchored at the accretion shock and slowly dribbling into the accretion disk, which actually shows you the evolution of jets in this inner region. So out here, this is an earlier time, this is a slightly later time, and you can see that the jet has moved out here. At a slightly later time, the jet has moved out here, the jet has moved out here, and the simulation is ongoing. But the bottom line is that any sort of magnetic activity that you throw into the system actually provides for the evolution of jets in this system. And with that, I can actually that's what I have, and that's also when I've run out of time, so I'll go ahead and stop.